Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to discuss the topic of improper priors for Poisson likelihoods. Basically, what I would like you to see is that we can think of improper priors as a limit case of legit prior distributions. And by legit prior distributions, what I mean are probability distributions that integrate to 1. Okay? Okay, let's begin. So, as I said, we are going to be discussing this improper priors, right? This topic of improper priors, centering our attention for data with a Poisson likelihood. Okay. So let's write down the likelihood for a single observation. We can easily generalize the ideas that we're going to be discussing here to a sample of size n. So likelihood for one observation. So one observation y, the probability of observing y given mu, right? We know that the probability mass function for a Poisson with parameter mu is mu to the power y divided by y factorial e to the negative mu. And the support for this probability mass function is 0, 1, 2, 3, so on. Okay, and mu has to be positive. Okay, so now let's use a conjugate prior. Okay, we know that the conjugate prior for the parameter mu in this case is the gamma distribution family. Okay, so our prior is given in this particular case by a gamma with parameters v and r, and the PDF, the probability density function, looks something like this. Okay, and well, the support for that PDF is positive mu's. Okay, and then we know that it's going to work, right? We already know that it's going to work for Poisson likelihoods, and we already know that the posterior will also be a member of the gamma distribution family, right? That's why we say that the gamma prior is a conjugate prior because the posterior belongs to the same family. Okay. So now we have probability of well, mu given y. We can think about the posterior along those lines. And we know, let's use the proportionality symbol, that what we're going to have in this case is proportional to this expression, right? So again, we have a member of the gamma distribution family. Okay, so this happens to be a gamma. R star, the new parameter for the posterior, is going to be y plus r. V star is going to be the old v plus 1. Okay, so all good thus far, right? Okay, but in this video we're going to be paying particular attention to the prior. Okay, now let's talk about a particular case in this gamma prior family. Okay, consider the case consider the case when r equals 1. And again, we are talking about a particular case for the gamma prior, right? So particular case of this gamma prior family. So when r equals 1, let's see what happens with the expression of the prior. You have v to the power r, right? So that's v to the power 1 gamma, function evaluated at 1. You have mu to the 1 minus 1 power. So as you can see, gamma evaluated at 1 is the same, right, as 0 factorial. So that's just a 1. V to the power 1, that's the same as v. And mu to the power 1 minus 1, that's mu to the power of 0, then that's just a 1. So in the end, what we're going to have is just this. And as you can see, that reduces to an exponential distribution with parameter v, right? Okay, so note this is an exponential random variable with parameter, or the PDF, right? This is the PDF of an exponential random variable with parameter v. Okay. So, something that is going to be also useful in our discussion is recalling what is the expressions that we can use to find the mean and the variance of a gamma random variable, right? So mean of gamma with parameters r and v happens to be r divided by v, and the variance of a gamma random variable with parameters r and v is going to be r divided by v squared. And this is variance, right? Variance. Okay. So when r equals 1, what we have is that the mean is going to be just 1 over v. Let me just write it down like this. Mean is going to be 1 over v. And the variance, right, variance will be 1 over v squared, or in other words 1 over v, the whole thing squared. Agreed? Okay. So what we're going to be doing next is we're going to see what happens to the aspect of the PDF of an exponential as v changes. Okay, we're going to see what happens if we make this guy v vary. Okay, so we will do this using R. Okay, so since we're going to be using R to play around with these gamma distributions, it would be a good idea to find out what's the expression that R uses for gamma distributions. So let's type help the gamma, as in gamma distribution, right? So let's find out. Here we have the expression that R uses for the PDF. 1 over s to the power of a, the gamma function evaluated at a, x to the power a minus 1, e to the power minus x divided by s. So, as you can see, right, we must have the expression of our gamma with parameters v and r. It's here. If you compare that to the one that R uses, it's different, right? It's a different way of expressing the PDF. Note that the expected value using that expression for a gamma distribution, instead of being R divided by V, like in our case, is going to be A times S, and the variance is going to be A times S squared. But if we compare, right, the expressions of these two different expressions for the PDF of gamma, right, the correspondence that we're going to have is this, that their A equals our R, right, and our R is their A, right, and that S happens to be the same as 1 over V. Okay, so let's write that down. Okay, and by the way, they refer to A as the shape parameter and S as the scale parameter. Okay, so let's write that down. This is as far as the way R does things with this, right? Shape equals A, and scale equals S, and the correspondence that we're going to have is this, that A equals R and S equals 1 over V. Okay, this is going to be important when we do the interpretation of what we're going to be seeing when we study the behavior of the PDFs as V changes. Okay? Okay. So, when A equals, let's see, when A equals 1, well, right, we're going to have an exponential, right? And using the expression that they have here, right, the expression that they have here for the expected value is s and s squared, right? Mean equals s and variance equals s squared. And then we're going to end up with what we have here, right? Since we are saying that we have that relationship here, we have exactly what we had here with our expression, the one that we use from our textbook, 1 over v squared. Okay, so we are in agreement. Okay? Okay. So, but we're going to be doing things the way R does things. Okay? So we're going to be using that scale parameter instead of v. So let's see what happens when s equals 1. Okay? And note that if s, the scale parameter, equals 1, that's equivalent to v being just 1 as well, right? So we're going to have a mean of 1 and a variance of 1. Okay? Okay. So let's play around with that PDF. First, we know that the support of gamma distributions is from 0 to infinity, right? Right? All real, all positive real numbers, and 0 as well, right? So all non-negative real numbers. So let's create a sequence that goes, say, from 0 to 100, and let's have a distance of 0.01 between the members of our sequence. Okay, and then we, as I said, we're going to use the expression that R uses, but we know that there's a correspondence between their parameter s, right, their scale parameter, and our v. Okay, okay. So y1, I'm going to be evaluating the gamma distribution, right, at these points x. Remember that the shape parameter is their a, and in that case our a, well, their a and our r is the same, so what we have here is that shape will be 1, and what we want to see is what happens when scale equals 1, meaning s equals 1, which is equivalent to having v equal to 1 as well. Okay? So again, that would be a gamma with parameters 1 and s equal to 1, so 1, 1, and that's a gamma with a mean of 1 and variance equal to 1. Okay? Okay, so now let's plot that guy. Let's see. Let me just restrict our attention to the following interval from 0 to 50. Okay, and we know that this guy is going to be between 0 and 1, right? Because it's going to be e to the negative, well, when you evaluate at 0, e to the negative 0, that's e to the 0, that's just 1, right? And from there, you have a decreasing exponential, okay? So something that looks like this, okay? And we could title that one, title exponential with scale 1. Okay. Okay. Now let's increase the value of s. Okay. Now instead of using value s equal to 1, right? Let's use 10. That would mean that we have an exponential with mean 10 and variance 100, right? So we have more variability than before. Let's see what happens when we do that. Oops, not what I want here. That's what I want. Let me create another one, right? Let me call it y2. And as I said, we're going to be increasing the value of the parameter s. Okay. Let's see what it looks like. Can you see that now this guy is flatter, right? Before we had something that was like this. Now we have something that looks like this, right? We can go back to the one we had before, so you can see the difference, right? We went from this to something like this, flatter. Okay, and that would be an exponential with a scale parameter equal to 10, right? Let's keep going. How about we try with a scale parameter of 100 instead of 10? So let's evaluate. And again, going back to this, if s equals 100, we have a random variable with a mean 100, but with a variance of 100 squared. So that's 10,000, right? So we have a lot of variability around that mean of 100. Let's see what happens. See, it's really flat, really close to 0, right? So we could use a magnifying glass, and that's why I introduced this y-lim, right? The limit for the y-axis, right? So let's modify that. How about, I think that 0.1 should work in this case. So like this, it looks almost like a horizontal line that goes through 0, right? But if we use kind of a magnifying glass, we go, oh yeah, it's a really small value. We basically have here almost like a line, right, with a really small slope, right? Okay, so let's keep going. How about now we increase that parameter s, the scale parameter, from 100 to say about 10,000. Okay, so that would mean that in that case we would have a random variable with a mean of 10,000, and then the variance would be 10,000 squared. So we have a huge variability. Okay. So now, if we just used the original scale 1, again, it looks like basically a flat line, right? But again, we could use some sort of a magnifying glass, and yeah, maybe in this case we need something rather small. Let's try with 0.0001. Let's see if that works. Oh, no, what I need here is y4, right? Yeah, y4 is the one that I want, right? So can you see that here, yeah, basically have almost like a, a flat line, right? But we have a really, really small slope that goes from 0 to 50, right? So if we used the original scale, which was from 0 to 1, you see it like this, going from 0 to 50, and you could go beyond that, right? Do it up to 100 as we initially had, right? And yeah, you can see that it's basically flat, right? And when we, made the vertical more restricted to smaller numbers, still we see that it's basically a flat line, right? So what I want you to see is that what we have there is that an exponential prior, which is what we have here, with a big value of x, looks very flat, right? Almost like uniform, right? A uniform over the interval from 0 to infinity. So we could say that our prior could be approximated by something that looks like this, right? Let me just say this just to make sure that you don't forget. So as we could see, an exponential prior with a huge or a big value, because it wasn't that huge, it was 10,000 I believe, with a big value of s, looks very flat. So so we could say that our prior could be approximated by, and let me use that notation, P of mu could be approximated by something that looks like this. Our exponential, remember that our exponential goes from 0 to infinity, right? But we could approximate it by something that is like a uniform, right? Over the interval 1 over c, right? That would be the expression for a uniform over the following interval, if mu lives between 0 and c, right? Okay, and what we're thinking here is for a huge c. Okay, so we could also think about this guy as something that is proportional to just one constant 1, right? So finally, what I want you to note is this. Note if we used, you know, a prior that is p of mu equal to 1 over the interval from 0 to infinity, well, in that case, the following integral, right, the integral from 0 to infinity of our prior, this guy, with respect to mu, doesn't exist. Right? You could say that this integral would be infinite, right? So it doesn't exist, right? So that's why, right, this kind of prior is called improper, okay? Because its integral doesn't equal 1, okay? So, however, note that if we applied Bayes' theorem using that improper prior, which would be, you know, just a1, right? Once you do this, posterior is prior times likelihood, right? Since your prior is just a constant of 1, right? The only thing that matters is your likelihood, and then that product is going to be, you know, a legit probability distribution. It's going to integrate to 1. Make sense? Okay, so basically that's what I wanted you to see. Okay, let's summarize what we did here. What I wanted you to see here is that you could think of these guys, improper priors, like limit cases of legit probability density functions. In this case, you could think of this improper prior like a limit case for an exponential, right, with a huge parameter s, right? Or if you think in terms of that parameter, if s is huge, v has to be really, really small. Make sense? But the idea is still there, right? That improper priors could be thought of as limit cases for legit probability prior distributions. Okay? And then when you use them, the thing is that even when you are using an improper prior, the posterior will be a legit posterior distribution, meaning a probability distribution that integrates to 1. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.